Okay, welcome students. In this video, we're going to finish up Chapter 2. Chapter 2, if you remember, is about nuclear chemistry. I always like to finish this chapter by talking about the Big Bang. Okay, it's a very important topic in science, and we're going to see how it relates to chemistry throughout this comic. Anyway, I'm not really into comics, but this is the best thing that I've found out there that explains the Big Bang Theory and how it relates to chemistry. It does a great job. So I hope that you are following along in your student workbook where this comic is found. Okay? And so I'm hoping that it will make sense to you. We're going to talk about the Big Bang. What is it? What happened because of it? Where do all the elements come from? We're going to talk about where galaxies come from, where stars come from, where planets come from. And all these things should hopefully kind of make sense when we're done with this comic. So anyway, let's get started. I'd like to start talking about the Big Bang with an equation that we learned last time. You guys remember this equation? Did we talk about it? Who came up with it? Einstein did. Einstein was the first person to figure this out, and he says that E, what is E, guys? Energy is equal to mass defect times speed of light squared. So he was the first person to kind of explain, and if you think about it this way, it's kind of cool. Energy can be converted into what? Mass. So we can get something from nothing? Sort of. Energy can be converted into mass, right? Can mass also be converted into energy?
Yes.
Yeah. That's what makes this topic so cool, is that before we were here, this planet was here, this galaxy was here, what was there here?
Nothing.
Nothing. Nothing. Well, the Big Bang says that there was this event, a long time ago. All the energy in the universe converged at a single point and blew up. Big Bang. Creative name, right?
Yeah.
Big Bang. So it blew up, and all that energy was converted into what?
Mass.
Mass. And so we formed elements that had mass. And all these elements form different compounds, and all of that stuff is here. That's what makes up you. That's what makes up this counter. That's what makes up this pen that I'm holding. Right? Can all be traced back to the Big Bang. And so everything that we discuss in science and in chemistry, it's obviously very important to study the Big Bang. So that's what this whole thing is about. This whole comic is going to help us understand the Big Bang. Okay, let's just start. We're going to read one kind of little box and explain it. So it might take us some time to get through these few pages of comics, but hopefully by the time we're done, it will all make sense. Okay, let's start. It says here, this is Owl. He says, "Greetings, I am the alchemist. I'm here to talk about where the scientists think elements came from." Do you guys get it? This little owl saying, "Get it? Alchemist?"
Oh.
Right? Remember the Penny Lab? The Penny Lab. Why did we do that one? Because what? How did chemistry start?
Alchemy.
By alchemists. Yeah, alchemy is taking ordinary metals into something that looks more valuable, right? Like gold, right? But were they really doing that? No. So that's why we did that Penny Lab. That's how chemistry got its start. Anyway, he says, "Get it, alchemist?" And then this owl, "Okay, yeah, I think they get it." And then this owl says, maybe we'll learn how to make gold." Okay. So let's finish up saying what the big owl said, though. He said, "The story starts with the Big Bang about 15 billion years ago. The periodic table was empty. It was just a possibility waiting to happen. So we're going to talk about the periodic table and how the elements came into existence. So 15 billion years ago, what elements did we have?
Nothing.
Nothing. Okay? It was nothing. There was no elements. So, how long ago did the Big Bang happen? 15 billion years ago. 15 billion years ago, the Big Bang happened. Okay, so then suddenly, bang! Let me see if I can scroll down a little bit so we can read that part at the bottom. Oh no, this is what happened before. Let me see if I can fix it. Okay. Oh, now my writing's gone. Let me clear it. Okay. Then suddenly, bang, all the matter in the universe exploded. Exploded from a single point. All the energy in the whole universe just exploded from a single point. At first, the universe was too hot for matter to become at all organized. So, when things get hot, guys, what happens to the speed of molecules? Yeah, they speed up. And was it really hot? Do you think it was really hot after the Big Bang? Very hot. So things were just flying around at really fast speeds. Nothing was organized. But then it says, within a few seconds, the protons, neutrons, and electrons formed. So protons were able to form, neutrons and electrons. And then what formed after that? And then so did hydrogen atoms. So what was the first atom in the universe? Hydrogen. And basically, the whole universe, okay? If this circle represents the whole universe, it was full of what?
Hydrogen.
Just a bunch of hydrogen atoms. A lot of hydrogen atoms. Okay, in fact, even today, the most abundant element in our universe is what? Hydrogen. By far, the most abundant element in our universe is still hydrogen. Okay, and that's because it was the first one right after the Big Bang to form. Okay, so that was within a few seconds after the Big Bang. Now let's keep reading. It says within the first 3 minutes, then we have this box here. Let's see if we can understand this box, okay? What's one? It's got one proton, and they're moving closer together. What kind of nuclear reaction takes two small atoms? Fusion. Okay, this is nuclear fusion. And then what happened here in this box? Pow! Is there a lot of energy released in nuclear fusion reactions? Yes. And so in this box here, number 3, it says, whoa, I feel like a whole new element. Why does he feel like a whole new element? Because it is. What element were they pushing together right here? Hydrogen plus hydrogen. If we look at the periodic table, what's the atomic number of hydrogen? 1. What's 1 plus 1? 2. What element did we make here, guys? Helium. That's why it feels like a whole new element, because it is a whole new element. Okay, so this was within the first 3 minutes after the Big Bang. What elements did we have in the universe? Hydrogen and helium. So 3 minutes after the Big Bang, the periodic table looked just like this. Hydrogen and helium. So now if we draw our universe 3 minutes after the Big Bang, what do we got? Hydrogen and helium. Just a bunch of hydrogen and helium. All of it. So, what do you think the second most abundant element in the universe is? If hydrogen is the most abundant, what's the second most abundant? Helium. Helium is the second most abundant, and that's still true today. So, okay, so we're good. We had the Big Bang, hydrogen formed. Protons, neutrons, electrons formed, then hydrogen formed. Then a few minutes later, were things flying around really fast right after the Big Bang? Yeah, extremely fast. And that's what you need in order for fusion to take place. So these hydrogen atoms slammed together, nuclear fusion reactions were occurring, making helium. So our periodic table at this point is empty except for the first two elements, hydrogen, helium. We good? Okay. Let's see. I'm going to erase this and scroll down again. Let me see if I can find a better way to scroll down. Okay. Here we are. Let's continue on. It says hydrogen atoms slam together in a nuclear reaction. What nuclear reaction was it, guys? Fusion. Resulting in nucleosynthesis. There's a fancy word. If synthesis means to make something, what does nucleosynthesis mean? To make a new nuclei, right? So did we make a new nucleus here? Yeah, that's the new nucleus, which is helium, right? So that's what nucleosynthesis means. Okay, and then it says, then for millions of years, the universe was just a rapidly expanding cloud of hydrogen and helium with no other elements. Okay, so for millions of years went by. What was the universe made of? Hydrogen, helium. Okay, millions of years went by, just hydrogen, helium. Okay, let's continue on. Okay, the top of the next page. Okay, it says because of gravitational attraction between atoms. Now let's stop there for a second. Gravitational attraction. How does do you guys know how gravity works? Well, yeah, I guess you let go of this pen, what's going to happen? It falls, right? It's kind of this force that acts on things with mass. Good job. So if you have mass, do you have a gravitational field? Yeah. Sure. Even our bodies do. But when we drop this pen, how come the pen doesn't fall toward your body?
It's very weak.
It's very weak compared to the gravitational field of the Earth. The Earth is way more massive. But anything with mass has a gravitational field or a gravitational attraction. So if the universe at this point was just hydrogen and helium, okay, well, gravity started to act on these elements because they did have mass. And gravity started at this part of the universe started pulling them together. And this part of the universe started pulling a whole bunch of hydrogen and helium together. And same with this part of the universe. It started pulling them together. And let's keep reading. The expanding cloud of the universe gradually broke up. Just like I drew here, it was gradually breaking up. Into what? Into galaxies. Okay, so this, I don't know, what galaxy do we live in?
Milky Way.
Milky Way. That might be the Milky Way galaxy. Does anybody know what galaxy is closest to us? Andromeda galaxy, okay? And there's, how many galaxies are there?
Too many to count.
There's just an incredible number of galaxies, okay? So what caused the galaxies, guys? What caused the galaxies? Gravity was acting on these clouds of hydrogen and helium and pulling them into like this circular, kind of fragmented cloud of dust of just hydrogen and helium, cloud of gas. And so it pulled them into those diverging galaxies. So it shows over here just a whole bunch of galaxies. Okay? Well, let's keep reading because we still just have hydrogen and helium. We know the periodic table's got, how many? Over 100 elements. So we've got to figure out where they come from. Okay. So let's keep reading. Some 5 billion years after the Big Bang, about 100 billion galaxies had formed. The process of fragmentation continued within each galactic gas cloud, forming billions of what? Stars. Okay, so there's a new one. We formed galaxies, but it says that this process kept happening, and there's this gas cloud, and it forms stars. Let's read about how the stars form. Okay, It says patches of hydrogen and helium. That's what I tried to show you right here. There's a patch of hydrogen and helium here, and here, and here. It says it gradually became organized by gravity. So gravity's, pulling them close to the, just kind of pulling them together really, really tightly into separate concentrations of such great density and pressure that they burst into fiery fusion. What formed right here? What is this? It's a star. Okay, so inside these galaxies, because the gravity is pulling them in so tight to the center, these hydrogen atoms come real close to each other, and there's very high temperatures. They start slamming into each other, and what happens there? Nuclear fusion. And when that happens a lot, they burst into fiery fusion and makes a star. That's how a star burns. That's how our sun is burning. Right now, hydrogen atoms are slamming together. That releases a lot of energy, and it burns. Lucky for us, right? We can still feel the heat even though we're a long ways away. We can see the light from it. And that's a good thing. Okay, so let's read the comic. It says here, fusion, push. He says, I am pushing. What are they pushing together, guys? One proton and one proton. What element is that? Hydrogen. Okay, they're trying to push them together. Fuse. So nuclear fusion happened. And then he says, that had quite a kick. How come they're blown backwards? Yeah, they formed helium. Does that release a lot of energy? Absolutely, and that kind of blew them backwards and blew them down. So that's how the stars were made. Okay, so now we've got these patches of hydrogen and helium inside the galaxies making stars. How many stars are there? Just an incredible number. Yeah, just an incredible number of stars. So there's billions and billions, and there's billions and billions of galaxies out there. So, okay, are we good to that point? Okay, but so far, how many elements have we made? Two. We got to get a little bit. We got to learn a little bit more. Let's find out where the elements come from a little bit. Okay, let's read this last part. It says, and so long, long ago, whoops. There we go again. I keep doing that. Okay, so we're right here. And so long, long ago, the stars became what alchemists on Earth, much more recently, could only dreamed of, crucibles, in which one element could be transformed into another. But the alchemists could hardly have dreamed of such staggering amount of energy required to drive the alchemy of stars. Okay, so this alchemist right here, he's like, is there any heat source powerful enough? On Earth, is there, guys? Look at this little Al. He's like, hello? And what's he pointing at? The sun. Are the temperatures high enough on the sun in order to do nuclear fusion? Yes. And then this other Al, what does he say? Good luck. Yeah. So can we do nuclear fusion in a controlled manner here on Earth? No, the temperatures have to be way, way higher than anything that could possibly control it. And so this guy, is he going to be able to make gold? No, he's not going to make gold. But with nuclear fusion. So, and that's why that little Allie's like, yeah, good luck, right? Okay. So, but stars, can a star make gold?
Yes.
Absolutely. That's where it comes from. So let's get on with it, with the story, and let's see if we can make sense of this. So we still only have two elements, hydrogen, helium. Okay. Next page. Follow along. It says pressure and friction in condensing clouds of hydrogen and helium had to bring the temperature to 10 million degrees Celsius for the first stars to ignite. We're talking about temperatures in the cores, the center of stars. And this little guy, he says, that's 5.5 million degrees Fahrenheit. 5.5 million. Incredible temperature inside the core of the stars. And then this owl says, our own sun is 1.5 times that hot. It converts 700 million tons of hydrogen into helium each second. Here are a few stellar nuclear reactions. So it's going to show us the nuclear reactions that happen inside stars. But I wanted to kind of point this out. How much hydrogen is being converted to helium on our sun every second? It said it right here. 700 million tons. Now in this area, we're familiar with ton bells. You know how big the ton bell is, right?
Yeah.
Well, most of them don't even weigh a ton. A ton is 2,000 pounds. And yet our sun is converting 700 million tons of hydrogen into helium every what? Every second. That's an incredible amount of hydrogen that's being converted into helium. And that's what's driving the heat and the energy of our sun. It's giving us. Yeah?
How do they measure helium in weight? Because it's like...
Well, I mean, if you get enough of it, you can actually weigh it out. It has a mass, right? It has a mass. And so we know the mass of a helium atom is what, guys? 4.00 AMUs. As we learn more in chemistry, we'll teach you how to go from that to actually grams. And then once you get to grams, you can go to pounds and tons. But anyway, it's just an incredible amount of hydrogen that's being fused together on the surface of the sun to make helium. Okay, so these are the nuclear reactions. I want you to look at them. They're going to be important. If you wanted to make helium, what would you do? Well, you have to add 2 hydrogens. What's 1 plus 1? 2. And that element is helium. Does it release a lot of energy? Yes. Okay. Well, what if you had a helium and a helium atom? And if temperatures were hot enough, which they are inside the star, you slam them together and fuse them. What are we going to make? Well, in this case, we made a helium and how many hydrogens? 2 hydrogens. Okay. And a lot of energy. So, this is what happens in small or below average sized stars. Our sun exactly fits into this category. Hydrogen is burning by nuclear fusion and it's making helium. Okay, now let's go to more massive stars because our sun is pretty small. There's bigger ones out there. You can find a lot bigger stars in the universe. Okay, so let's read it. The more massive the star, the higher its core temperature can climb. And when you have higher temperatures, the temperature goes up, you can fuse more elements together, larger elements. Okay, so this happens in larger stars. What's 2 plus 2, guys? 4. And what element did we make? Be, what is it, guys? Beryllium. So that's beryllium is made by fusing two heliums together. 2 plus 2 is 4. Okay, let's see what 4 plus 2 is. What's 4 plus 2? 6. 6 protons is what element? Carbon. So that's how the carbon atom is made. Is that the only way to make carbon? What if you fused hydrogen and boron together? What would you make? Carbon. 5 plus 1 is 6, so you make carbon. There's a lot of. What if you had 2 lithiums and fused them together?
Carbon.
Make carbon. Okay, and so inside stars, we're making what? New elements. Okay, let's go on one more. What's 6 plus 2? 8. And what element is that? Oxygen. So a carbon, and if you fuse that to a helium atom, you make oxygen. So this is how the elements were made. Nuclear fusion inside what? Inside stars. Okay. And so on, it says. Okay, let's delete this writing and move on with the comic. Okay. This bottom one, it says, several billion years after the Big Bang, and several billion years before the present, the periodic table looked like this. Okay, so it's filled up to this point, to this element. What is Fe? You guys know what it is? That's iron. Okay? So this is as far as nucleosynthesis in the core of stars can go. But the periodic table was far from full, and the most of the elements were trapped inside of the stars. So these elements weren't just free to go out into the universe. They were trapped inside the stars. So stars burning can produce up to and including iron. But how do we get these other elements here? Where do these elements come from? Okay, so we filled it up to iron, which is atomic number is 26. How do we make the other ones?
Star has to die.
Okay, yeah, let's read about it. Good. Okay, but he says, but wait, the death of stars means the life for chemistry. And you've got this diagram here. This is a star. What's pointing inward, guys?
Gravity.
Gravity. What's pointing out? Pressure. Okay, so let's read this. It'll explain it. Throughout the life of every star, the inward force of gravity is at odds with the outward force of pressure. Stars balance between collapse and explosion throughout their life. When you have nuclear fusion going on, does it want to blow up? And there's pressure outward, right? Sure, and that's where you get this pressure. Nuclear fusion is wanting it to blow up. What's holding the star together, though? Gravity. Because they're so massive, there's a lot of gravity pulling it together. And so there's this kind of balance throughout the life of the star. This pressure is being counterbalanced by gravity, holding it together. And that continues throughout the life of the star until the end of the life cycle of that star. At the end of the star, something happens. Okay, let's find out what happens. Okay. It says, at some point, though, a star uses up its fuel, and either gravity or pressure must prevail. So when it's done burning, when our sun is done and there's no more hydrogen to fuse together, its life cycle is coming to an end. It's got one of two things will happen. Either pressure will win out or gravity will win out. Okay? So it says here, we're at this point. If a star is extremely massive, gravity wins. The star collapses into a black hole, an intensely powerful center of gravitational attraction from which not even light can escape. So it's a huge star, it's very massive. Gravity will pull it in, and gravity wins out. And so it collapses on itself and forms a what, guys? Forms a black hole. How come they're called black holes? Can't see them, they're black. Why are they black? Because light can't even escape it. And it pulls in objects. They get close to it, it'll pull it in because it's a very strong gravitational field around black holes. And they've been watching these, they know where some are in the universe. And so, yeah, that's how black holes are formed. Super massive stars just collapse in on themselves at the end of their life cycle. Okay, but what if they're not super massive stars? What if they're kind of, I don't know, just medium sized or whatever? Okay? But in other stars, pressure wins out. They explode into so-called supernovas. You guys have heard of that? A supernova is the term that they give when a star explodes. Okay, and pressure wins out. Gravity can't contain it anymore, and pressure just builds and it blows up. What's going to happen to the temperature of that star when it goes and becomes a supernova? Yeah, the temperature is just going to climb even higher, which allows us to do what? Even more nuclear fusion with larger elements. And so larger elements can go through nuclear fusion now. Let's scroll down and figure the rest of the story out. Okay. Let's read it together. So supernovas allow several important things to happen. They provide conditions to synthesize even more elements, bringing the table up to this point. Okay, so now we've got all the elements filled out up to this point right here. This element is uranium. So when a star blows up, it's called a supernova. Temperatures get so hot that even larger elements are able to go through nuclear fusion reactions. And you can make up to and including uranium, which is atomic number is 92. Okay. Now, we still have some empty parts of the periodic table. If you look at the periodic table that you have, it goes all the way up to 118. So where do those elements come from? Okay, let's find out. I think it will explain. Okay, supernovas. Oh, this is an important point. Very important. Supernovas blow their surface atoms into outer space, liberating, making them free. The elements are able to just leave the star and they just fly out. So Au, gold, Cu, uranium, potassium, copper, iron, all these elements that we know are just thrown into outer space. And they continue until they do what? Until they hit something or come into a gravitational field of another object that pulls them in, right? Well, what if there was a big chunk of elements right here, and they're slowly building up because of gravity, more and more elements are pulled in. What can you form? What could you form? We're talking a lot of them, but what could you form? Couldn't you form a planet? Yeah? The star explodes, all this material is just thrown out into outer space. It slowly builds more and more gravity is pulling it in, more and more elements. If you look at the anatomy of Earth, the core, what elements make up the core of Earth?
Some
Iron and nickel, these heavy and these dense elements formed in the core because gravity's pulling them in. What's on the outer surface or the crust or even our atmosphere? The lighter elements, right? They're less dense. So Earth is kind of organized according to the more dense in the core, less dense elements on the outside. And that's because of gravity. Also another important thing, why are all planets in the universe that we have ever seen, what shape are they?
Circle.
Well, circle's two-dimensional.
Sphere.
They're sphere. They're spherical. Why are they always in a ball shape?
Because gravity's pulling from all sides.
Gravity's pulling from all sides. Will we ever encounter a planet that looks like a cube?
That'd be
No.
really cool, though.
I mean, if some guy just felt like chiseling an entire planet, maybe.
Maybe, okay, you got me there. If some guy chiseled it. But no, gravity pulls from all sides. So like a snowball, if you put snow on all sides, you're going to form a sphere. And that's exactly why all the planets that we know and have ever seen and will ever see are going to be round. Okay? And that's where they came from. So we can trace back all the elements on Earth to what, guys? To a star. What about the elements that make up you? They come from where? A star. Originally, a star must have blew up somewhere, thrown those elements throughout outer space, and Earth picked them up because it's growing gravitational field. Right? Okay? And so that's where the elements come from on the periodic table. Let's keep reading because there's some more things that we got to understand. Okay, we're to this point. It says, finally, in the relative quiet outside of stars, chemistry can really take off. Instead of nuclear reactions, chemical reactions can occur. And it gives us an example of a chemical reaction. So up to this point in chemistry, we've been talking about nuclear reactions. Nuclear reactions make new what? New elements. But we're going to talk for the rest of the year about chemical reactions. How are chemical reactions different? Well, let's look. They're taking hydrogen and adding it to oxygen to make what? Water. Did we make new elements?
No.
No, we made a new compound. It's made up of more than one element, but we didn't make a new element, we just added them together and made a new compound. So that's the difference between a nuclear reaction and a chemical one. Also, chemical reactions, a lot less energy are involved. Nuclear reactions, huge amounts of energy, temperatures have to be very high. Chemical reactions we can do here on Earth because the temperatures don't have to be so high. But we're not making new elements, we're making new compounds. Okay? Okay, let's keep reading. And that's the general story of how the elements came to be, except 15 billion years after the Big Bang, on a small planet called Earth, human scientists began to produce tiny amounts of new, unstable elements. And so you've now got it filled in. Okay, the periodic table is now filled in. If you notice this periodic table, they're white after uranium. That means every isotope of these elements are radioactive. These are formed in a lab. Scientists are forming them in a lab. They're so unstable, they lie off the band of stability. They decay in milliseconds, and they're gone. They give off radiation, they're gone. Become something stable. So that's how all the elements on the periodic table came into existence. Okay, so let's continue on. So which do you think would be easier and cheaper? Synthesizing a brand new batch of gold from other elements, or just digging the old gold out of the ground? What do you guys think? Is it easier to make gold with nuclear fusion, or mine it out of the ground?
Depends on how global the people are.
But we're not gullible. We're not going to buy it unless it's real gold. What's easier, guys?
Digging it up.
Okay, let's see what they find out. This little Allie's like, I'll just go get my pick and shovel. He's going to go mine it, right? Because he's smart enough. He knows the difference. Okay? Nuclear fusion. You can make gold with nuclear fusion. But are temperatures that high here on Earth? No. Can you form it inside stars and supernova when it blows up? Sure. But not here on Earth. Okay? Let's see what this guy says. He says, better yet, let's just forget about gold and see what we can make using chemical reactions. Maybe we'll make something as good as gold. So he's gonna do chemical reactions where the temperature just doesn't have to be as hot. All right. That is the story of the Big Bang, how the elements came into existence, how galaxies formed, how stars formed, how planets formed. And hopefully that helps you understand how important nuclear reactions are in chemistry. Before I stop the video, I just wanted to take a second and review how the elements came into existence. So a few seconds after the Big Bang, what was the whole universe? What element?
Hydrogen.
Just hydrogen. A few minutes after the Big Bang, what elements were there? Hydrogen and then helium. Okay, then it condensed into galaxies, and then gravity pulled it in even tighter and formed stars. Inside stars, you can form up to and including what?
Iron.
Yeah, iron. So inside stars, you can form up to iron. How do you get all the other elements that are heavier than that? Yeah, when this star blows up, supernova happens, you can form up to and including uranium. Well, how do you form all the elements after that?
Chemical reactions.
In a lab, right? They're so unstable, they're so radioactive, you form in a lab. So hopefully that helps you see where the elements came from. And I hope you understand more about the Big Bang and how it relates to chemistry. All right, in your student workbook, there's a worksheet called the Big Bang Comic Review. I would like you to complete that now that you know a little bit about the Big Bang. And hopefully that helped.